Now let's look at another way of combining two vectors. We have vector A in pink and vector B in blue, and we're going to form something called the dot product. Now the dot product is best understood geometrically. So what we do is we take the component of vector A that is in the direction of vector B and we multiply it by the length of B. So that's a lot of words. Let's have a look and see what we mean. So what part of vector A is in the direction of vector B? Well, there's two blocks. So the x component of vector A has got length 2 and that's in the direction of vector B. So we take the 2 here and we multiply it by the length of vector B, which is 4. So we get 2 times 4, which is 8. And there you can see the component of vector A that is in the direction of vector B. Now in order to get this length here, what we do is we form the cosine of this angle. So we could say x upon A is equal to cos of theta. So you can say that the length x is A cos theta. So what we do is we multiply A cos theta, which is this little pink line, with the length B. So the dot product A dot B is going to be the length of A times the length of B cos theta. So let's look at this mathematically. So as I've just said there, we can form the dot product A dot B by taking the length of vector A, multiplying it by the length of vector B, and then multiplying it by the cos of the angle between them. Now, we don't have access to the cosine function with our integer library, but there's an easier way for us to generate the dot product. Now I'm not going to go through a proof of this in this video. If you're interested, I have another course called Mathematics, a Graphical Approach, and I go into vectors in detail and I go through this proof. But we can find this vector dot product A dot B by simply multiplying the components together. So we take the first component of vector A, multiply it by the first component of vector B, and then we add on the second component of A multiplied by the second component of B, and so on and so forth. And this will generate the vector product. And you can see here I've just put the fact that our x upon A is going to be cos theta, so x is equal to A cos theta. So in this little example that we've drawn here, we can see that the dot product A dot B is going to be the length A cos theta, which is our length of 2, times the length of vector B, which is 4. So 2 times 4 is 8. So before we go on and we have a look at the program, let's just quickly take a couple of minutes and we'll see why we bother with the dot product in the first place. Let's take a couple of minutes to look and see why the dot product is useful. Now the first thing we're going to look at is qualitative. So let's say, for example, this vector A in pink was sitting at 90 degrees to the vector B in blue. So vector A runs up along this line here. So it means that the angle between them is 90 degrees. We say that these vectors are orthogonal. So if we were to form the dot product between these two vectors, then the cos of the angle 90 degrees is 0, so the dot product would be 0. So if we form the dot product between two vectors that are orthogonal, we get the value of 0. And it's useful in mathematics to try and work out whether vectors are in fact orthogonal. So this is a useful quality of the dot product. Another thing to note that is if the vector A was in the direction of vector B completely, then the angle theta would be an angle of 0 degrees. The cos of 0 is 1, so it means that the dot product in that case would just be the same as the length of vector A times the length of vector B. So it means that in these two instances we can determine whether the vectors are orthogonal or parallel, and to be able to do that is a useful thing in mathematics. Now the other thing to note about the qualitative aspect is that If the value for the dot product is a positive value, it means that there's going to be a component of this vector in the direction of this vector here. Because we're going to have a positive times a positive that would give us a positive value. Or equally, if both of them were in this direction, we would have a negative times a negative, which would give us a positive value. So we're really saying that if it was a positive value for the dot product, then we know there's a component of this vector A in the direction of B. But if we had a negative value for the dot product, it would mean that there would be a component of this vector here, which would actually be in this direction. So for example, the vector would be sitting over in this quadrant here. So depending on whether the dot product gives us a value of 0, or whether it gives us a maximum value, or whether it gives us a positive or negative value, it tells us something about how the vector A is related to the vector B. So that's the first thing that we looked at, is kind of qualitative, but the other one is purely quantitative, meaning that the actual number 2 times 4 gives us a value of 8. Although it seems quite arbitrary, we take the component of this vector in this direction times this vector and we form a single number. And we might think to ourselves, well, what is the point of the actual number 8? But this is very useful to us in some branches of mathematics, and especially in physics. The prime example that we use is whenever we're working out the work done on a body whenever you move it from one position to another. So whenever we apply a force to a body, the only component of the force that does any work is in the direction of travel of the object. So if we had an object sitting here and it's travelling in this direction, and we apply a force at an angle, the only component of that force is the component in the direction of travel, and we can get that from the dot product. So that is an actual quantitative reason for using it. So overall, the dot product is a very useful form of vector manipulation. Just one other thing to state here, we often call it the scalar product, or we also say that it's a form of vector multiplication. So you might as well ask, how can it be defined as a multiplication? Well, actual multiplication that you learn at high school is very limited. And if we were to look at how we actually define multiplication generally within mathematics, you'll find that the vector product here actually falls within that definition of multiplication. So that's all we want to talk about as far as the dot product is concerned. Let's go ahead and we will actually look at the code and then put it into the CPU and see it working. Now we have our two pieces of code. The one on the right is a calling function, the one on the left is a subroutine. So the one on the right is going to have two arrays here, which are in fact two vectors. We could call that vector A and vector B if you want. It's up to yourself how you like to write your code. So we'll use the same example that we used in the example we just looked at. So we're going to have the first vector here is going to be along 2 and up 3, so that's vector A, and the other vector is along 4 and up 0, so that's the vector B. So whenever we form the dot product, we multiply the components, so it's going to be 2 times 4, which is 8, plus 3 times 0, which is 0, just gives us the final answer of 8. It's that simple. But of course, if we wanted to, we could add in more components. We know that the length of the vector is 2, and we're going to form the dot product, so we'll call that dot, and all we do is set aside one memory location, because it's just a single number, or what we call a scalar quantity. We've got the actual routine here called math underscore vect underscore dot, and I've set aside a memory position within the RAM for the start of the ROM for the start of the subroutine. So we're going to push the array 1, push array 2, push the length, and then push the position where we want to return the result. And then we can jump into the subroutine It jumps into the subroutine, works through the subroutine, and whenever it finishes, it jumps back out here to the end, and that's it finished. So let's go through the subroutine. And again, a lot of these are very similar to what's gone before, so we don't want to spend too much time in it. You can always get access to the actual files, and you can run it all for yourself, and you can see it all running in minute detail. So whenever we jump into the subroutine, we're going to do the housekeeping. So we take all the values for the registers that we use, and we take a copy of them, stick them in memory somewhere, and we then start popping off the values that we require. And you can see we're popping off into R4, index register R3 and R2. Now we also go through this process of clearing off register R5, because register R5 contains a running value for the A1, B1, A2, B2, and whenever we finish up, we're going to have a value in there. So what we want to do is make sure that whenever we come in for the next time we use this subroutine, that value is cleared off. Otherwise it's going to corrupt the next usage of this subroutine. Now we begin here and we load the value that's pointed to R2 into R0. So we're just putting the contents of our A1 in R0. So we put 2 into R0, and then the next line it puts the value 4 into R1. We do the multiplications, and then we do the addition with the contents of register R5. So register R5, as I said, starts off with a value of 0. I then increment R2 and R3, so increment so that it's now pointing to the value 3, and we increment so it now points to the value of 0. And then we decrement the index register to tell it that we've worked through one iteration. So eventually, after working through all these iterations, whenever the index register comes down to 0, the comparison is true. It jumps if it's equal to the return. So it jumps down here, and then whenever we return, what we do is we then place the final result, which is in R5, into the correct place in memory, and the correct place in memory is held within register R4. So we're going to save it into dot, and then we come down and we finish off the housekeeping. We're going to return the registers all back to their original values, so it's almost like we have never been there in the first place. And then we can jump to the return address, so we jump up here and we head off to the end line, and that's the end of the program. And thing to note here is down here as well, I have to declare all of the variables that I use locally within the subroutine. So we've got all of the positions for the variables, so for the temporary locations for the values of the registers, and also the dot, the length, and the return address. Okay, but you've seen that before in previous videos. So that's the program. Let's go ahead and we will load it into the CPU, and we will see it running. So I have loaded the subroutine into the ROM and the code into the RAM. Let's see it running. So go simulate and tick enabled. So it's going to be 2 times 4, which will give us a value of 8. So it's setting everything up at the moment, and I've ran it at full speed here. So it shouldn't take too long for it to run through. So that's the 2 times 4 is 8. 3 times the 0 is the 0. It's then cleared off all of the values in the registers and put them back to the original values. And that's it, finished the code with a little red end light coming on. So we can stop this, and we will go in and just have a quick look and see whereabouts in memory the information is. So you can see here it's at 0500. So we've got the vector A, which is 23, and then the vector B, which is 40. We found the dot product. 2 times the value of 4 is 8, and 3 times the value of 0 is 0. So it's 8 plus 0. Now this value here is just the length of the vector, which we know is 2. The final answer is in this position here, which is the value of 8. So it works fine, and that's us covered in some reasonable detail the dot product. We're nearing the end of our vector manipulations. In the next video, we will go on and look at the cross product. Now there might be another couple of vector manipulations I may well add in later on, but that'll be pretty much us done, and then we can start moving on to matrices. So thank you for listening. I'll get you on the next video. Goodbye.